Good morning. Happy Monday. How's everybody doing today? Welcome, welcome. If you're here, say hello. Also, thank you to those who came out to the Science Expo. I got to at least meet a few of you, so put a face to the name, and I always love doing that. So thanks for coming by and saying hi, and I hope you had a fun time, and we'll probably do it again in Josephine County, hopefully in the spring. But we need to chat about what we learned and then get details for our next event. So thanks again. All right. I don't have any announcements. I think everything is going smoothly for the most part. And again, just reach out to me by email if you have questions. And I wanted to start off with this question in the homework because it's the one that I either saw that was the most left blank or the most questions on. So let's go over all of these and talk about possible acceptable answers. And so it asks, gives one example of each of the following. And it says an isotope of carbon 12. What was an isotope? What did that mean? And if you're in the chat, you can answer. But basically, right, it has to be defined by its protons, right? And it has to be a carbon. So that's what we're saying with an isotope. So that means it has to be 6 protons. And so any isotope of carbon, and you could make up isotopes as well. Yeah. Again, I don't know if these exist. So any isotope of carbon, go crazy here. So these exist, 13 and 14. And the rest I'm just kind of making up as any example, right? So you can't have it have a mass less than 6, right? Because our mass, we need 6. And 6 is probably a little crazy. Even 8 is a little crazy. Just, again, coming up with examples. And so what does it mean by isoelectronic? What is that term? Anyone know? So isoelectronic means same number of electrons. Let's put number of electrons. And it's neutral carbon. So basically we just need 12 electrons. And so we could either, I would say let's go on either side of the periodic table. Where's my, oops. Let me grab a periodic table from last week's notes. I think I need to post last week's notes still, so I haven't forgotten. Just been a busy week. All right, so here's our periodic table. And so if we're looking at carbon, so carbon 12 here, and so this has 12 electrons, well, we could go back to boron, right? So if we're looking at, however, if we do 11 boron, well, neutral 11 boron, right, just has 6, sorry, we need something with 6 electrons for carbon, right? So boron has 5 electrons, but if we make it 11 boron negative, or it doesn't have to be 11, so we could do 10 boron as well. So 10 boron, it's neutral, so 5, so still has 5 electrons, so then we make it negative, so that would be 6. We could also go the other way, so nitrogen. So of course nitrogen has 7 electrons if it's just neutral, and we could pick nitrogen 14. And then if we want to make it isoelectronic to carbon 12, it would have to be nitrogen plus. Let's put those answers down. So 11 boron negative, 10 boron negative, both of those are fine. 14 nitrogen positive, could be 15 nitrogen. Again, we're just looking at electrons, so it doesn't matter. We could go over to oxygen, so 16 oxygen, then that would have to be 2 plus to be isoelectronic, and kind of so forth. Right, so I think these two people figured out. So same thing with this one. So this wasn't too bad, maybe. So an atom that has the same number of protons. This was actually the same answer as A. So this is really A. And so then, right, you could go through all the different isotopes. And then D. So this one could be tricky. So an atom that has the same number of neutrons as carbon 12. So then it's saying, well, we need anything with 6 neutrons. And so now we have to do some math. So we could go down. So looking at our periodic table, right, we could even take lithium. So we do lithium, but then with 6 neutrons, so 3 plus 6, that'd be 9 lithium. And again, charge doesn't matter. So it's asking about neutrons, so you can make these ions or not. And let's go over. So what if we want to do boron? So boron, we want 6 neutrons, so 5 plus 6. So then it has to be 11 boron as our answer. Let's pick another one. What if we wanted oxygen? So oxygen with 6 neutrons, so 8 plus 6 is 14. So that would be 14 oxygen. We could do the same with nitrogen. So nitrogen is proton or atomic number 7. So proton 7. So 7 plus 6 is 13. So 13 nitrogen. And again, you could have other possibilities for this one. Any questions on that one? And then I think the last one that people had issues on was this one. And this was because of this term nucleons. And nucleons means the total number of neutrons plus protons. So basically, we're saying, right, it has to add up to 12. So we could do, 12 boron, 12 lithium. So this would be crazy, right? Something that has, so this would have 3 protons and 9 neutrons. Again, don't know if this exists, but just a possibility. 12 oxygen would work. We could, 12 nitrogen. Let's see, 12. What elements am I missing? 12 nitrogen. I already did 12 nitrogen. 12 beryllium. There we go. So on and on and on. Does that clarify all those now? All right. So kind of where we're going with this chapter. And we're going to be heading into chemical bonds today, so how things bond. But we're going to be referencing kind of this chapter 2 a lot. So if you have questions about chapter 2, if we need to go back to electron configuration, let me know, because there were some questions about that. And, I had some questions of, I don't really understand electron configuration, but electron configuration, right? We're just trying to figure out where are the electrons. And, this is really a complicated question in a lot of senses. And to truly answer that, right, we need Schrodinger. So that's really what it boils down to. Except we have all these other ways with our patterns and then kind of seeing what compounds they form to describe the nature of the atom. And then the electron configuration is really just fundamentally telling us, how do they fill in? What orbitals are they in and they occupy? And those orbitals correspond to shapes. And so again, we'll kind of review back and forth and build upon. So just ask questions. All right, so let's take our overview approach right now. And so we have, well, compounds are composed of atoms held together by chemical bonds. And so this chapter is going to be starting to define what are chemical bonds, how do they share electrons or transfer electrons. And so we'll see that these chemical bonds result from the attractions between the charged particles that compose them. And so we'll look into three types: ionic, covalent, and we'll at least talk about metallic. And so now let's look at ionic versus covalent. And so ionic, this is our ionic structure. And so right away, you should notice that this ionic structure is kind of, it's a cube in itself. And then it just kind of repeats patterns. And so it's not really a discrete molecule. So we can see that. So it's just repeating. So they're in a 1-to-1 ratio. And again, we'll look into deeper how this happens. And so kind of comparing the structures, so salts tend to be very brittle, and that's because of their crystal lattice structure. Again, with these repeating units, so they have opposite charges all surrounding them. And so then when they break, so you can think of like table salt, or if you have those salt lamps, right? If they break, it's going to shatter. It's very brittle. It's kind of crystalline. And we take a look at these covalent molecules. And well, this is ice, but you probably know, right? Ice melts. So these covalent bonds, some of them tend to be like liquids or gases. But then notice they're all discrete little molecules. Well, that's different. And so now let's start taking a deeper look. We have ionic bonds. So an ionic bond occurs between a metal atom and a non-metal. And so let's look at that. So, right, that means it's something from this side of the periodic table in general. So this is kind of your standard group 1, group 2 metal complexes. And then we can also see complexes formed with transition metals, but these get a little tricky. So all these can have variable oxidation states. So we're going to kind of ignore them for now, but they're still metals, but we'll revisit them. So we're mainly thinking of metals, and then they're going to add with non-metals. So anything right on this stair step generally. So all these are non-metals. And so what's interesting about the ionic bond is, again, it's a transfer of electrons. And so we'll look at that. And so our metal always tends to become our cation. And again, we'll kind of explain why it has that tendency. It'll be related to chapter 2. And then our non-metal will become an anion, so our negatively charged particle. All right, so let's take a look at sodium chloride. But before we do that, so let's review from last time. So let's see if we can draw or write out our electron configuration of sodium and calcium, or chlorine. Oh my gosh. So if you're in the chat, go ahead and write out your electron configuration if you can. And let's start going through it together. You can also pull up your chapter 2 notes. And so this is where you want, right, your periodic table. You want it to be marked. So right now you can reference it. And so we said we started with our 1s. So write 1s1, or we could have written neon if we wanted to take our shorthand approach. And so I'll write the full thing out. And so 1s2, because we fill all those electrons in, and then we go back. So now we're starting 2s2, 2p6, and then now sodium's on that next row, so 3s1. Or again, we could have written it neon 3s1. Is that what everybody got? And just flag me down if we don't understand this. And so keep in mind, right, chemistry kind of builds upon each other, especially early on. It's very cumulative and you have to understand what's going on. So just reach out for help if you're lost. And now let's do chlorine. So chlorine is on the same row. So let's continue filling it in. Starting again, so 1s2, 2s2, 2p6, so 3s2, and then 3p, 1, 2, 3, 4, 5. Again, we can double check. So 2, 4, 10, 12, so 17 electrons. So that matches for chlorine. We could have written it with our abbreviated form. So neon 3s2. Three P5. And so looking at this is where we want to translate, again, our electron configuration to our Lewis dot structures. I kind of touched on that last time. And so let's break this down again, just so we're all on the same page. So these are all, right, our core electrons for sodium. Right, that is our core electrons. And leaving our 3s1 as our valence. And so we can go back to chapter 2. Just as a reminder, okay, that's right. That's why we said those alkali metals were really reactive, because they have this NS1 pattern. So yes, that makes sense. So sodium has one valence electron. But what we're learning, and again, why it's reactive, is that it's going to go ahead and give up this electron, right? So it's actually going to donate it to chlorine. And so I'll just write out its Lewis dot structure, again, representing our 3s1. We have one of these sides is our s orbital. I just put one electron in there. But this is ready to pop off and actually just transfer over to chlorine. And so again, looking at chlorine, we can do the same thing. And so again, these are our core electrons. And so now we're really close to having a fulfilled octet on chlorine. So these are our valence electrons. So let's fill out our Lewis dot structures. So 2 in the S first, and then we distribute 5 in our 3 Ps. So 1, 2, 3, 4, 5. So it looks something like this. We could represent it with our boxes. So instead we write 3p. So fill in our S, 1, 2, 3, 4, 5. And so again, we have 7 valence electrons for chlorine, right? 7 valence electrons here as well. And so what's going to happen is, so when they get together in a reaction, so sodium is actually going to give up its electron. So it's going to donate it to chlorine. So now let's kind of rewrite that. So sodium plus our chlorine. So now I'm just rewriting our Lewis dot structure. And again, I'm just showing how our electron's going to be given up. And then that leaves us with sodium plus, and then our chlorine is negative, and we want to draw in all those electrons. And then now we can say that both are actually satisfied by the octet rule. And so now let's practice another thing, and that's going to be writing our electron configurations of these charged compounds. So take a minute to do that. So what's sodium plus's electron configuration? And you could write it in the abbreviated form. And then what is chlorine minus's? Then for sodium plus, our electron configuration ends up being neon, since we lost our 3s1, or we could write it out. So 1s2, 2s2, 2p6, and again, satisfied by octet rule, so it's happy. And so let's look at chlorine. So let's start with neon for that one. 3s2, 3p6. And so now chlorine has an octet with our 8 valence electrons. So our chlorine -1 anion is happy as well. Any questions on that? And of course, right, we saw they form oppositely charged ions, which again are attracted to one another and are held together by those electrostatic forces. And so here is again just another representation of that. And obviously, what's kind of cool as well is, of course, sodium metal. You would obviously not want to consume that. And again, we mentioned, right, really water reactive. And then if we add it with chlorine gas, again, you don't want to consume chlorine gas. That's highly toxic. But you put these two toxic compounds together and you form your table salt. And so we've been practicing then our Lewis dot structures. And again, this is just a bonding theory. So it helps us to illustrate kind of simple bonding concepts and help us with our ionic compounds. And it is useful for our covalent compounds as well. And so like we've been practicing, we've just been seeing how to represent our electron configuration with our Lewis dot structures. Again, same thing with potassium. So it's our alkali metal. And again, it follows that 4s1 pattern. And then we're going to see it has a tendency, so it can make potassium chloride. Same thing like sodium. So everything right in group 1, notice makes a 1-to-1 ratio. And so with that, that's where we get these charges from. So notice, right, all our alkali metals have a +1 charge. So again, think back to that NS1 pattern. So if they have one valence electron, they're going to have a tendency to lose that valence electron, making our +1 charge. So this +1, we can also think of as our oxidation state. And so notice is, again, the charge balances. So if we look at our halogens, well, if they're only one away, so they are NP5, all of these, well, they're just one away from NP6 having a fulfilled octet. So they're all going to make -1 ions, anions. So I see that with chlorine, of course, but fluorine does the same thing, bromine and iodine. And so now we see that kind of repeated. So if we look around, so our alkali earth, right, NS2. So when they make compounds, so they make a 2+ charge. So now we need 2 equivalents of, let's just say, chlorine to balance that charge out. This chart also shows like a few other metals that tend to have just one oxidation state. So scandium and yttrium tend to be in 3+. We should probably also add on here zinc. Zinc is always 2+. And then silver is 1+. And again, the rest of these can have different oxidation states. And then aluminum is 3+. And then notice, so we skip over this one. This one gets weird. Your periodic table might have this 4+4- here. So keep that in mind. But so right, we could actually make this compound. So this would be lithium carbide. But you don't often see too many examples of group 4. It can happen. But notice, right, there's a switch. So notice with group 4, it could either lose 4 electrons or gain 4 electrons. And again, they also tend to be involved in a lot of covalent compounds instead. And then let's look at group 5 here. So this is nitride. So we can make lithium nitride. So this is a compound. This is a cool compound, actually. So I mentioned that inorganic chemists sometimes use like glove boxes to keep things safe from reacting with air and oxygen. But the problem is, so oftentimes these glove boxes have nitrogen, since that's a lot cheaper than using argon, I mean. But the problem is lithium exposed to nitrogen over time makes lithium nitride, which doesn't really do too much. It just forms this blue sheen on your lithium. I'm trying to find an actual picture of lithium. Okay, the internet has disappointed me. I don't know why I can't just find a little picture of some lithium with that blue sheen on it. Oh well. And so we also have phosphides. So sodium phosphide, for example, moving over to group 6. Again, in that NP4 pattern. So, right, they just need 2 electrons to fulfill that octet. hence why they're all -2 oxidation state. And so we can make beryllium oxide as an example. And so those, if we have a -2 charge and a +2 charge, they're already in a 1-to-1 ratio, so they're balanced. Magnesium sulfide, just as an example. And so this is selenide and telluride. And then again, our fluorides. So sodium fluoride, sodium chloride, sodium bromide, sodium iodide are all examples. And so this is also cool. I think you have videos of this, but it's always fun to see these in person if you can. So the conductivity of sodium chloride. And so our ionic compounds, again, they're just held together by our electrostatic forces. So sodium chloride. So that means in water, they disassociate into our sodium ions and chlorine ions. And so you can think about this with your water as well. So sometimes it's flavored with different salts or like magnesium salts or phosphates or carbonates. So that's what gives it its flavor. So all those ions are floating around. But now with these ions, they can allow electricity to be conducted. And so basically they're in your beaker floating around. So you have your wire connecting up to your light bulb here and some sort of power source. But basically your connection is broken. Sorry, my light bulb sucks. But then if we have an ionic compound in here with all these ions floating, and remember they're floating, they're moving, and it's that movement. So the movement is key. So it's that movement that allows our electrons then to be transported, and that completes the circuit. So any ionic compound will light up a light bulb. Now, if you have something like sugar, so sugar is a molecule, and so sugar will not conduct electricity. And so we'll go over these formulas a little bit more, but we're starting to notice, so there are always positive and negative ions, but then in our chemical formula, the sum of the charges has to equal the sum of the charges of the negative ions such that the whole thing is neutral. Unless, of course, right, you're working with a charged particle, then of course, right, the sum of your charges of your positive and your negative charges equals the whole sum of your molecule. And then our formula is just our smallest whole number ratio of ions. Any questions? So now we want to look at how to write our formulas and their names. So first we're going to start with our metal that only forms one type of ions. Then we'll look at how to name our variable metals. And so again, right, this is going to be our alkali metals or alkaline earth, zinc, aluminum, and silver. Oh. And so to name them, for these simple ones, right, we just name our metal and then plus our prefix of our ending, and then we change the ending to "ide." And so for this one, right, it's sodium and then chloride. I shouldn't have put prefix. That's not a good word. So anion, but then we change the ending to ide. So then sodium chloride. So try these two, or these three. We'll go over them. So MgO, what would that be? You can put your answer in the chat. That'd be magnesium oxide. And so notice right there, balance. You could look at their oxidation state. So magnesium, that would be 2+. Oxygen is -2. They're already in the 1-to-1 ratio. And I'll go ahead and show this trick. So I always call this the swap trick. And so what I mean is I just start my scratch work for finding out the formula. And for this one, it's a little trivial, but we'll see how it works. And so I have magnesium 2+ for its oxidation state, and then oxygen 2- for its oxidation state. And then for our swap trick, we just swap these numbers. Since this is a mathematically most basic solution, because what we're trying to do is get our total charge, right? 0 is equal to 2+ times our x plus 2- times y. So to solve for x and y, it's easiest to just swap these values. However, in this case, and this is why I showed it now, is, well, right, we have a 2 to 2. Well, we want the number to be the simplest and the smallest whole number ratio. So if you were to get Mg2O2, right, you simplify it back down to just MgO, which is what we started with. And so CaF2, that's calcium fluoride. And we could go back. So calcium 2+, fluorine -1. So now let's do our swap trick again. And so that gives us our formula back out, CaF2. And then this last one, this is just aluminum oxide. And again, let's rederive this formula. So aluminum, we said is 3+. Go back to here too, right? 3+. Oxygen, -2. Let's do our swap trick. And that gives us back our balance formula, aluminum 2O3. And so this swap trick only works for our neutral compounds. And you'd probably have to do a little bit of math if you had a charged compound, but we won't see those for a minute here. And so now this is just another chart trying to help show you different oxidation states. So again, we see our group 1 always has +1, group 2 always 2+. I don't know why scandium and yttrium are left off in this one. Again, there's almost no rhyme or reason sometimes. And then this is not an exhaustive list either. It's just showing you kind of the common ones you'll see. So you have chromium 3 plus, chromium 6 plus, but again, chromium could be other states as well. Same thing with manganese. It seems a little misleading that it's here. It's is still variable oxidation state. So you could have 3 plus, 4 plus, 5 plus, 7 plus. All those are possible. Same thing with iron. So it's just showing kind of the most common ones are 2 and 3. And they're also ignoring all these other metals, which also, again, have variable oxidation states. And what's kind of confusing is they throw silver and zinc in this mix, but these are considered to only have one oxidation state. So don't confuse those. And then it shows you nickel and platinum, right? But these are variable oxidation states. And then all these are pretty explanatory and in the pattern that we've seen. Questions? All right, let's look at our multivalent metals now. And so how do we name, right, all those other ones? So all our transition metals essentially, and there's some other ones. So I'll point out which ones. But how do we name them? And so lucky for y'all, it is a much easier naming system than even when I was in school, which gets further away every day, but still wasn't that long ago. And so now let's look. And so all we do is, well, now we still name our metal ion like before, but now we put their oxidation state, so their charge, in parentheses. Now we're looking down, so let's look. So we can have this formula, Cu2O. Well, let's back that out. I say reverse swap trick because you'll have to identify what oxidation state copper is in. And so if we back it out, right, there's kind of our 1 here, 1 plus. And so when we back it out, the first thing you want to check, especially when you have an element like oxygen, is does it match with what it should be? And so oxygen is always -2. And in this case, it does, right? So we don't need to do any multiplication, binding factors to make oxygen correct. And so again, if oxygen is -2, that means copper is 1 plus. And so that's how we get copper 1 oxide. So it's not referring to the number of coppers, right? But referring to the oxidation state. And so this is where students get messed up all the time, is that people want to say that this is copper 2, right? Because there's 2, but no, that's not the case. It's referring to the oxidation state. So whatever you need to do, a big star that the Roman numeral, right, is our oxidation state. And so as long as you can remember that, it's pretty simple. So then the CuO, so let's practice this one, CuO. Let's do our reverse swap trick, as we would say. And so this is a good scenario of what I was referring to. So you kind of reverse it out, and then you get oxygen is -1. Wait, that doesn't make sense. So that means we have to multiply everything by 2. And then, so if it's everything times 2, then that means, right, it's copper 2 plus, and then oxygen -2, which gives us our copper 2 oxide. And then what's nice, so if you compare this, and the reason why I'm showing this is so you see how the older naming convention is, and just in case you see like a chemical or a textbook and it's using these older names, you know what it's referring to. And so it used to be that the lower oxidation states, so in this case, it's kind of the two most common ones like chromium, 2 plus and 3 plus. So the lower oxidation state takes the ose form, the higher takes the ic. You can see that with iron 2 and 3. But again, we don't do that. So it's a lot simpler just to use a Roman numeral, and that's a lot more helpful and universal. So same thing, we have copper, 1 plus, 2 plus. And so notice, so tin, mercury, lead. So here are some odd ones as well. So you have tin 2 plus, 4 plus. And let's also note on their thallium. And so you might want to mark that somewhere. I'm going to go ahead and highlight it. Let's see what's a good color. So our thallium, lead, tin. So those tend to have multiple oxidation states as well. Mercury. All right, questions. So again, we don't need to know the older naming system. I'm not testing you on that. This is just more for your information. So now take a look at these 4 examples. And I'm going to give everyone a minute or so to work on them. And again, if you're watching, this would be a good time to pause. All right, I'm going to keep moving on live. Again, if you need more time, just pause it if you're watching later. If you're live in the chat, flag me down. And so we have this one. So I'm going to do our reverse swap trick again. So reversing back, so we get 2 plus. So that's probably my oxidation state of iron, right? And we back out. So chlorine is -1. So just kind of do your sanity check, right? That your charges balance out. We'll have 1 iron, that's 2 plus. And then a -2 times 2, so that's -2. Yes, they balance. And so that means we can write it iron and then 2 for oxidation state, chloride. So that means this next one, so reverse backing it out, that gives me iron 3 chloride. All right, watch this next one. This is a good example. So we have SNO2. So let's back it out. Except we get 2 plus and 1 negative. And so -1 is not the oxidation state of oxygen. So we need to multiply everything times 2. So in reality, it's 4 plus and -2. So again, do your sanity check. -2 times 2, well, that's -4. And 4 times 1, so that's +4. So yes, that balances out. And so now I know that this is 10 4. So Roman numeral is for 4 is this. So tin 4 oxide. And so be careful, going back and forth with the swap trick and reverse swap trick with these, again, multiples of 2, especially with oxygen. So this is where, again, you just have to be cautious. And then this last one, CON. So this is one where we have to look at what nitrogen's charge is. So -3. And they're in a 1-to-1 ratio. So cobalt has to be 3 plus. So this is cobalt 3 nitride. Any questions about those? And if any questions come up when you're doing your homework and checking your answers, again, just send me an email and I can help clarify. And so now let's cover these polyatomics. And so what is a polyatomic ion? Let's define that. And so a polyatomic ion is what I was referring to, and it is a covalently held together molecule with a charge. And it could be something simple like hydroxide. So if we draw what hydroxide looks like, this is hydroxide, except it has a -1 charge. So it would be located on the oxygen here, like I've drawn it. So this is a polyatomic. So poly, right, just 2 or more. That's one example. And we will kind of get into how to draw them as we go through this course. Let me draw carbonate out for you. This is carbonate. So again, it has an overall -2 charge. All these are covalently held. It's just the oxygens are carrying a -1 charge each. So that's the polyatomic. So at this moment in time, we don't need to know how to draw them, although it's coming in later chapters. We just want to appreciate that, okay, I have a name and it corresponds to some charged compound. Let me see. Do I have another? This is a good polyatomic cheat. So on the next slide over, it has a bunch of charges. So this is useful. I'm trying to remind myself what order they're in because these are the same. They're just arranged by different ways. And now I forgot why. So we have I was trying to find acetate on there. So this is a good list. So acetate, ammonium. Let me point out a couple of other ones. So if you notice, you don't have too many positive polyatomics. So I'll point out ammonium. That's one of your few positively charged ones. I could draw out ammonium for you. So it just looks something like this: nitrogen with 4 hydrogens, and nitrogen is missing an electron, so it has a positive charge. Let's see what else is common. You might see acetates. Oh, the problem with acetate is it can be written in various ways as well. So acetate, let's draw out what it is since it's kind of important. So this is acetate, which is related to acetic acid, but this is acetate. But you can also see it written in other ways as well. So sometimes you see acetate written out as CH3COO negative. So just watch for that. That's a weird one. And this one's trying to show its structure more, and this one's just the simple formula. So just watch out for that one because you do see a lot of acetate, especially, we'll talk about it more when we do our bases and acids chapter at the very end of this quarter. So there's carbonates. So carbonates come up a lot, just commonly. We mentioned hydroxides. So hydroxides are bases, so they'll come up. And then we see a lot of nitrate. We see nitrates, but don't confuse them with nitrites. So nitrite has one less oxygen. And so I have worked with a bunch of nitrate salts. The nitrite salts just tend to be not as common. Same thing with phosphate and phosphite. So phosphate has more oxygens. It's PO4, 3 minus, and phosphite has one less. Same thing, sulfate, sulfite. So sulfate is more common at SO4, 2 negative. And then the sulfite has one less oxygen again. And so for your exam or quiz or whatever, I would just print this out, have this handy, because you're not going to memorize all these. And I don't expect you to. So have these handy as your cheat sheet. And then this will help you name it. So then the main thing you want to be concerned with is identifying your polyatomic. And again, your hint is that, well, there's not a lot of positive ones. So as soon as you see ammonium, right, that's a good key. But then when you're staring at your compound and then you're like, where's your metal? So, right, you have to identify where's your metal, and it's going to be group 1 or 2 or a transition. And then you want to look, well, is the rest of it a polyatomic? And you could have weird metal ones. So you do have chromate. So this is a polyatomic dichromate, and manganate and permanganate. So just watch out. There could be some weird ones. So let's give it a whirl. See if you can name these. So give everyone a little bit of time, or again, you could take this moment to pause. So if you're in the chat, again, post your answers and follow along. And so what do we get for this one? So you might have to find, right, your polyatomic. So CR2O7. Oh, here it is, Cr2O7. And it even matches with the charges, right? -2. Oh, that makes sense why we have two potassiums there. And so now we can name it. So we just name our metal, so potassium. And now we just state our polyatomic, so potassium dichromate. Not too bad. And so now this one, right, we identify our metal. So that's magnesium. That's our group 2. So we don't need to indicate any oxidation states. Then hydroxide. Okay, this last one could be tricky. So we have our metal, but now it's one of those metals with multiple oxidation states. NO3, go ahead and find that. Oh, there it is, nitrate. And it has a -1 charge normally, but there's 3 of them. And so, right, we could either do our reverse swap trick. So this is -1, right? So we could back this out. Well, that gives us iron 3 plus. So that works. Do a little sanity check. So -3 times 3 is -3. So yes, iron has to be 3 plus. And then remember, we write iron 3 for our oxidation state, nitrate. And then again, just sanity check. How do we rewrite the formula? So Fe3 plus, as we said it was iron 3. Nitrate, write out NO3, -1. Now swap trick time. And that gets us back out our iron 3 nitrate formula. And so you want to take some time with this. Do the homework, practice going back and forth, do it again if you need. If you want, additional help, I can find some resources. Just putting it out there, Everett Community College has a lot of online resources that you can find, and they post answers as well. And so you could do more practice with naming if you need. But practice, practice, practice. That's the big thing about chemistry is it does, take some time. Again, that's why I make it open note for y'all. But you at least want to practice, what you need to do and what resources you need, like these sheets. All right, now I feel like we've sped through this chapter. I'm just kind of looking ahead to what we have here. So I think I might save this for Wednesday. So we'll go back and do some practice. So I would say tune in Wednesday. If you can, we'll do some practice, right? Be here live so you can be practicing in the chat. But then the other thing we want to think about is questions for Wednesday. So what are you struggling with? What do you have issues with? Could also be lab related if something is confusing or the post-lab questions are confusing. Anything like that we can cover. And we can also do more electron configuration practice as well. Let's actually end with that. Let's do that because I know people were struggling with electron configuration. And let's make a new periodic table over here. We'll do more practice. And let's try some weird ones. So let's try europium for fun. And let's go over bismuth. I'll give everyone a minute or so. Again, this would be a time to pause then we'll go over it. Again, ask questions, email me questions, and I can cover them on the video as well. So let's walk through it together. Let's start with europium, and let's do our abbreviated electron configuration. So if we want to do that, we have to go back to the previous noble gas. So that looks like xenon. So xenon. And this is where it's good to write your marked periodic table. And so I may need to write a few markings for myself. So 3s, 4s, 5s, 6s, 7s. Oops. And then remembering, right? 3D, okay, 4D, right? 5D, 4F. So all these markers help me. So 2P, 3P, 4P, 5P. All right, so now I'm ready. So now we're at xenon. And so we go down 6s2, filling up in order. And then this is what we expect, right? So then 5D1, and then 4F1, 2, 3, 4, 5, 6. And so this might be one of those where, remember, we were discussing that there are 7F orbitals. So I might expect that it actually does not fill in the D, but so we would have some oddities there potentially. And so I'll write, right, this is our kind of expected. Again, if we fill normally. Another perfect answer, though, is again, if you recognize that, well, there's 7F orbitals, so it might be better if we do 4F7. And this is also correct. So both would be correct. And if, again, I know we take electronic tests. So if you run into this sort of situation, you can always email me and I can fix that. So both of those would be acceptable answers. And let's try our bismuth one then. And let's see. So again, previous noble gas. So we still have to start with xenon again. So now we're at xenon. So filling it up in order. So 55, 56. So 6s2. And then, okay, well, now I need to go through all. So if I can see, well, I'm going to fill up, right, 4F14. Then we're going to go back and fill up the 5Ds. So let's go ahead and do both of those. So 5D10, 4F14. And now we're back at 6P, 1, 2, 3. For bismuth. And these are usually considered the valence electrons. For these compounds, we usually kind of ignore all those. Any other questions or thoughts? So if there's a particular example too, like an electron configuration you're struggling with, or definitely email me and we can go over it. We can meet individually as well. Yeah, I am here for you. All right, this seems like a good place to stop. So, again, look ahead on tomorrow's, or not tomorrow's, but Wednesdays. So, we'll practice some naming and we'll go over this. So we haven't named this water compound, so we'll go over that. And any other questions we'll go over as well. All right, thanks for an awesome class. Again, I'll hang around in case there are any other questions, or again, just email me if there's any other personal questions, logistical questions, grades. I am here, I am responding. And if you don't hear from me in like 24 to 48 hours, definitely email me again. I usually don't let emails slip through the cracks, but sometimes can always miss one. All right, thanks again. I really appreciate y'all for being here. And I know many of you watch later, and I thank you for that as well. All right, enjoy the rest of your Monday. Have a great day. Thanks again.